Bonding in metals. Okay, we kind of talked about this at the beginning of the chapter. The electron C model. Here's our better explanation. Okay, so we saw that metals have low ionization energies. And the electron C model helps us to understand this. What happens in a metallic solid, and this could be a pure metal or it could be an alloy, which is a homogeneous mixture of metals. Each of the metal atoms donates one or more electrons to the electron C, the ocean of electrons, the pool. They're pooling their electrons. So we can think of sodium metal as being an array of sodium cations surrounded by this negative electron C. And the sodium cations, which would normally repel each other, are held together by their attraction to the negative C. Okay? This model explains the conductivity of metals. These electrons are not localized. They're not attached to a particular ion. They're just like a big pool of water, right? They can move. And so we can have conduction, which is the movement of electrons. It also explains malleability and ductility. Malleability means that you hit it with a hammer and it dents instead of shattering. Ductility means you can draw it into a wire. Those are things that are characteristic of metals. The reason that you can do that is because the attraction between the sodium ions and this sea of electron is in all directions. And so if you move one of the ions, we noted earlier that the distance between opposite charges has a big effect on how strong the attraction is. But here, because that sea of electrons is mobile, when you move the sodium, it doesn't affect the amount of attraction. And so you can hammer out metals and they just dent instead of shattering. This is kind of interesting. I won't test you on this. The Lewis structure of ozone. The ozone layer is in the news a lot, and it's important. Oxygen has a double bond. Ozone, O3, as we saw earlier, has weaker bonds. They're intermediate between single and double bonds, so like a 1.5 bond. So this harmful UV light that comes from the sun is strong enough to break the bonds in ozone, but it's not strong enough to break the double bond in oxygen. So what happens is these photons are absorbed by the ozone molecules. So they do not go through the ozone layer and come down and hit us. The ozone is decomposed into an oxygen molecule and an oxygen atom. This oxygen atom's not very stable. These guys are going to recombine to reform the ozone. And so the light from the sun is absorbed by the ozone, but the ozone is not destroyed by the light from the sun.
Does it make the ozone really hot then?
I think there's definitely some heat involved, but that's actually a good thing, because if we didn't have this insulating layer of atmosphere around us, our planet would be too cold for life, because there's just no heat out in outer space. And the reason that chlorofluorocarbons can destroy the ozone layer is because they mess up this reaction, the reforming of the ozone. Yay, we finished the chapter.